Okay, perfect. So just as a refresher, when we last left off, we completed calculating the formal charge on each of our atoms in this molecule. Now, continuing on, our next goal is to assign the molecular geometry and hybridization of each atom found in this molecule. So first and foremost, let's take a look at hybridization. So looking at this carbon, it has how many single bonds? How many sigma bonds does this carbon have? Or how many single bonds? 3. So it has 3 single bonds. You can also think of it as 3 charged spheres if you're using Chem 101 nomenclature. So then if we have 3 charged spheres, or 3 electron groups, what hybridization involves 3 charged spheres? Trigonal planar molecular geometry, sp2 hybridization. So this is sp2, and this carbon has a trigonal planar geometry. Okay. Let's continue on and let's take a look at the nitrogen atom. So looking at this nitrogen atom, how many charge spheres, how many single bonds does this nitrogen atom have connected to it? 2. And does this nitrogen have any lone pairs? No. So then with 2 charge spheres, what hybridization does it adopt? SP. Yep. So this is an SP hybridized nitrogen. And with 2 charged spheres, yes, linear geometry. Exactly right. Okay, now it's technically incorrect to assign hybridization to this nitrogen, and it doesn't necessarily need to hybridize. If you had to state a preferred hybridization for this nitrogen, given that it has 1 single bond and 2 sets of lone pairs, how many total charged spheres do we have? 3, yep. So we have 3 charged spheres. So what would the preferred hybridization of this nitrogen be? Not geometry, just hybridization. sp2, yep. It's not really correct to assign a geometry to this nitrogen, as geometry requires having multiple connected atoms to your atom, right? There's no bond angle to be had because there's no additional atom connected to this nitrogen. Okay, perfect. So we've assigned the hybridization, we've assigned the molecular geometry, and we've assigned the formal charges. You want to become very practiced at doing this kind of analysis on every molecule you'll encounter, as geometry and formal charges are critically important to assessing reactivity, molecular shape, and overall bond length and strength. Let's continue on. I'll be handling this next example, and first and foremost, we can generate this structure using the concepts we discussed associated with condensed formulas. We can read this formula from left to right and transcribe each of the given functional groups or bonding motifs in this molecule. And additionally, this NC indicates a unique bonding arrangement and a unique bonding motif that we discussed last class session. So looking at this, reading our formula from left to right, CH3. So what should we draw? Yes, exactly. A carbon with 3 hydrogens attached. Let me change the pen type to better accommodate this document. Okay. So we have a carbon with 3 hydrogens attached. Perfect. Following up on that, reading the next part of our formula, what should we draw? CH2, a carbon with how many hydrogens attached? 2. Okay, perfect. So far, so good. Now, this last functional group or this last bonding arrangement is slightly unique, but nonetheless, we can handle it using similar rules that we observed last class session. So an NC, okay? So what should we draw first and foremost? What is attached to this carbon? A nitrogen, yep. And then what is attached to that nitrogen? A carbon, okay? Perfect. So far, so good. Now, if we look at this bonding arrangement and we count the total number of electrons in this molecule, so for our 3 carbons, we have 12 electrons to work with. For our 5 hydrogens, so 1 times 5, we have 5 electrons to work with. And for our nitrogen atom, we have a total of 5 electrons to work with. Okay, perfect. So this gives us in total 22 electrons to generate a structure from. Looking at this current structure, we have 1, 2, 3, 4, 5, 6, 7, 8 bonds. So we've used up 16 electrons. Okay, so we have 6 electrons remaining. If our goal is to fulfill the octet of every single atom in this molecule, where should we start placing those 6 electrons? Where should we place those 6 electrons? Carbon and nitrogen. Okay, perfect. So let's start by placing them on nitrogen. And how many lone pairs does this nitrogen need? How many? Two lone pairs for a total of 4 electrons. So let's place those lone pairs. 1, 2, 3, 4. We now have 2 electrons remaining. Where do we place the last 2 electrons? On carbon. Okay. Now, we've used up all of our electrons. Does carbon have a complete octet? No. So what do we need to do? We need to take some of these lone pairs on nitrogen and move them down to form what? Double or triple bonds, right? Now, considering this carbon has 4 electrons, how many additional bonds does it need? 2 additional bonds for a total of 4 additional electrons. So let's erase these nitrogen lone pairs and let's form a triple bond. So have we now fulfilled the octet of every single atom in this molecule? Is the octet rule fulfilled? Yes. Okay, perfect. Is everyone comfortable with this Lewis structure so far? Is it okay if I erase this electron counting to free up some space? Okay, perfect. So let's erase our electron counting, and now let's focus on formal charges. Now, using our idea of pattern recognition, utilizing pattern recognition here, let's try to reduce the amount of work that we have to do. So looking at this carbon with 4 bonds, what have we established immediately before in this example? A carbon with 4 bonds has a formal charge of what? 0. Exactly. Okay. What about this carbon? Does this carbon also have 4 bonds and no lone pairs? So what's its formal charge? 0. See, pattern recognition can help save time. A nitrogen atom with 4 bonds and 0 lone pairs, just like this nitrogen atom down here, has a formal charge of what? +1. Yeah. Okay, the only unique calculation we have to do is this carbon with 3 bonds and 2 lone pair electrons. So carbon has a group number of 4. We have 3 bonds, as we've discussed. And how many lone pair electrons do we have? 2. So that gives us a formal charge of -1. So this carbon has a negative formal charge. This is known as an isocyanate functional group, and these things smell terrible. Okay, so with our formal charges assigned, let's now move to geometry and hybridization. Let's move to geometry and hybridization. So let's start with the leftmost carbon. So the carbon in the CH3 functional group. Okay, so how many charge spheres, how many single bonds and lone pairs are surrounding that carbon? 4. Okay, so we have 4 charge spheres. So what hybridization does this carbon adopt? For 4 charge spheres? sp3, exactly right. And what geometry is associated with 4 bonds and 0 lone pairs? Tetrahedral. Okay. Okay, perfect. Now, looking at this carbon in the CH2 functional group, does that carbon also have 4 bonds and 0 lone pairs? So does it have the same geometry and hybridization? Yes. Always try to utilize pattern recognition to reduce the amount of work that you have to actually think about. Okay, perfect. Now let's take a look at this nitrogen, and we can again use pattern recognition. Compare it to this nitrogen above. This bottom nitrogen has how many single bonds? 2. So how many charged spheres are around this central nitrogen? 2. And as we established previously, 2 charged spheres corresponds to what hybridization? sp. Yeah. So our nitrogen atom has 2 charged spheres, has an sp hybridization, and what geometry does it adopt? Linear. The real point I'm trying to drive home with this example is the more you can utilize pattern recognition and comparing a new example to a previously solved problem, the faster you can solve new problems. So always try to keep that in mind when you go through the homework assignments. Finally, looking at this carbon, how many charged spheres, how many single bonds and lone pairs are around this carbon? How many total charged spheres? 2, exactly. Has 2 charged spheres. So what hybridization would be most applicable to that carbon? sp, exactly. Perfect. So these are a set of diagnostic examples just to help me get a sense of how comfortable you are with the 101 material as we move forward in organic. Any questions on these 2 examples? Does it look familiar from 101 and 102? Okay. So let's talk a little bit about formal charges now. Let's talk a little bit about formal charges. And here, again, we're going to be using pattern recognition to our advantage. So let's start first and foremost with this carbon atom here. So taking a look at that carbon atom, how many bonds, how many lines are drawn attached to that carbon atom? 4. So this carbon atom has 4 bonds. Okay, and does it have any lone pairs attached? No. So using our formal charge rules, 4 for our group number minus 4 bonds gives us a formal charge of 0. So any carbon with 4 bonds and 0 lone pairs has a formal charge of 0. Using that idea, taking a look at this carbon here, does this central carbon also have 4 lines, 4 bonds drawn to it? Yes. So what's its formal charge going to be? 0. Okay, what about this carbon here? Does this carbon also have 4 bonds to it and 0 lone pairs? Yes. So what's its formal charge? 0. Okay, perfect. Now, we're going to really utilize pattern recognition to our advantage with this oxygen atom here. So we're going to have to do this calculation from scratch. So first and foremost, what is oxygen's group number? 6. Okay. How many bonds are drawn to this oxygen? 1. Okay. And how many lone pair electrons, how many dots are around this oxygen? 6. So what's our formal charge going to be? -1. And remember, as we discussed last class session, any oxygen with 1 bond and 3 lone pairs has a -1 formal charge. So looking at this oxygen, which conveniently enough has 1 bond and 3 lone pairs, what's its formal charge going to be? -1. Okay, perfect. Let's now take a look at this nitrogen right here. Have we solved a problem almost exactly identical to looking at this nitrogen? Is that a nitrogen with 4 bonds and 0 lone pairs? Yes. And what is the formal charge of that nitrogen going to be? +1. Just to reiterate, 5 minus 4 gives us +1. Perfect. Finally, let's close things out and let's look at this top oxygen here. So this top oxygen, what is our group number? 6, okay? How many bonds, how many lines are drawn to this oxygen? 2, okay? And how many lone pairs are on this oxygen? Oh, let me rephrase. How many lone pair electrons? 4, yep. So that gives us a formal charge of 0. So this oxygen has a formal charge of 0. Perfect. So we only had to do really 3 unique calculations. And some of these calculations we've done in solving previous problems. Okay, let's now look at this next example, which is a common intermediate in Friedel-Crafts acylation. So first and foremost, looking at this carbon. Does that carbon have 4 bonds and 0 lone pairs? Yeah. So what is its formal charge? 0. Just to reiterate, 4 minus 4 gives us 0. Okay, this oxygen here is a little bit unique. Let's do this calculation from scratch. So this oxygen has a group number of 6. How many bonds are attached to this oxygen? 3, yep. So 6 minus 3. And how many lone pair electrons do we have? 2. So that gives us a formal charge of +1. Okay. So the key point I want to make with this entire example is really try, whenever you're solving a new problem, to relate it to problems that you previously solved and tackled. It not only helps you save time, but pattern recognition is the key to quickly and efficiently getting a first look at a problem. Okay.
College. Just let you know everything is safe. You may return to your classrooms and resume class.
Okay, perfect. Okay, so any questions on the quiz before we, yes?
So in the bottom,
Yes.
When they're, I guess you could say the flames, are those signatures are carbon? Right?
Which ones?
The flames of the, because I've seen that in a couple of spots, like on the book or the homework, where it'll have the molecule run out like that.
Ah, yes, yes. We'll be talking more about bond. If you've been looking through the read, yes, each of these little intersections of 2 lines is representing a carbon atom. This is known as bond line notation and is an alternative way of expressing Lewis structures without having to explicitly draw every single hydrogen. Yeah, and we'll be talking about that more actually this session. Any other questions on the quiz? Yes.
Was it hydrogen or carbon? Because I had a similar. I mean, when I saw those blank ones, I was like, I don't know what that means.
So the intersection of these 2 lines is a carbon atom, and that carbon atom has any amount of hydrogens needed for it to reach a complete octet. We'll be talking more about this concept in actually this lecture. Okay, any other questions on this set before we start continuing on with our lecture content? The solution will be posted on Canvas shortly. Okay, so let's take a look and let's practice a little bit more on assigning formal charges using common bonding motifs. So let's take a look now and let's look at these following 2 examples. So first and foremost, let's take a look at this upper oxygen atom. Let's take a look at this upper oxygen atom. Let me switch the pen for this format. So looking at this upper oxygen atom, how many bonds are attached to this upper oxygen atom? How many bonds? 2. So we have 2 bonds. And how many lone pair electrons? 4. Yeah. 2 bonds plus 4 electrons. So performing one formal charge calculation, our formal charge would be 6 minus 2 minus 4 for a formal charge of 0. Okay? So any oxygen with 2 bonds and 4 lone pair electrons has a formal charge of 0. So looking at this next oxygen in this structure, what is the formal charge of this oxygen with 2 bonds and 4 lone pair electrons? What's the formal charge? 0. Exactly. Okay. As we have established time and time again, a carbon with 4 bonds and 0 lone pairs has a formal charge of what? 0. Yep. 4 minus 4 gives us a formal charge of 0. Likewise, a nitrogen with 4 bonds and 0 lone pairs has a formal charge of what? +1. Okay. Now, there's one other bonding motif that we have not yet seen. And in this case, we have a carbon with 3 bonds and how many lone pair electrons? How many dots do we see on this carbon? 2. Okay, so calculating our formal charge, 4 minus 3 minus 2, that gives us a formal charge of -1. So a carbon with 3 bonds and a lone pair is anionic, has a negative charge. Okay, So using this first example, what I'd like you now to do is to assign the formal charges on each non-hydrogen atom in the rightmost structure. And really try to utilize this idea of pattern recognition in formal charges. Yep, that's good so far. Yep, that's good. Any questions? No? Yeah, that's great. Any questions? Good, good. So, following up on this idea of pattern recognition, looking at the following carbon with a total of 4 bonds and 0 lone pairs, what's the formal charge going to be? 0. Okay, looking at this carbon with 3 bonds and 2 lone pair electrons, what's the formal charge? -1. As you can see, this carbon is exactly identical to the carbon in the leftmost example that we calculated the formal charge for. Okay, a nitrogen with 4 bonds and 0 lone pairs, what's the formal charge? Yep, +1. An oxygen with 3 lone pairs, 6 lone pair electrons, and 1 bond, what's the formal charge? -1. Yep. Okay, and then finally, an oxygen with 2 bonds and 4 lone pair electrons, 2 lone pairs, what's the formal charge? 0. I want you to be able to quickly assign formal charges as it helps us identify what species are potentially activated for certain chemical reactions, where electron density is potentially localized in our molecule, and it's really important to identify regions of localized electron density or localized charge as it helps us understand molecular shape and molecular reactivity. Okay. So let's do a few more examples. Let's do a few more examples, really just to drive home the point. I'll start us off with the first set. So, of course, a nitrogen with 4 bonds and 0 lone pairs will have a formal charge of +1. A carbon with 4 bonds and 0 lone pairs, 4 minus 4, gives us a formal charge of 0. This molecule, if you're taking biology classes, you may recognize as the fundamental backbone, the key structural motif found in an amino acid. Now, assigning formal charges, this carbon has a formal charge of 0, and this oxygen has a formal charge of 0. What about this oxygen up here with its 3 lone pairs and 1 bond? What's its formal charge? -1. Okay. So this is a unique compound in that it has both a positive and negative charge found in the molecule. Okay, I'll do one more example just to help us along. So both of these carbons, which have 4 bonds and 0 lone pairs, have a formal charge of 0. This carbon here with 3 bonds and 1 lone pair, performing our calculation, we have our group number of 4 minus 3 bonds and 2 lone pair electrons, gives us a formal charge of -1. In general, in most cases, if you see a lone pair localized on carbon, it will have a negative formal charge. Okay, what I'd like you now to do is to attempt assigning formal charges on these 6 molecules. These have been specifically chosen to encompass common intermediates or functional groups that you'll see later on in this class. So let's focus on assigning formal charges to the major non-hydrogen molecules. Any questions? Looks good so far. Yes, I'll be ready. Yes. Mhm. So what's the group number? So, so then how many bonds do you have? So this is known as an expanded octet structure. That's actually a lead into our next lecture. So, but following the formal charge rules, if we have a group number of 6 and 5 bonds, what are the formal charge? Yeah, exactly. So even though it's a unique bonding molecule, it still follows the same rule. Any questions? Looks good so far. Any questions? Any questions? Your assignments look good so far. Yes. Yep, that's perfectly. Yep, that's a carbon with 4 bonds attached to it. So it has a family charge. Yep. Any questions? Okay. So let's talk about a few of these examples, and let's go through and let's try to highlight their common significance in when you'll encounter these molecules throughout your courses. So first and foremost, this molecule here is a common organic base known as, in this case, this is dimethylamine anion. So looking at these carbons, each of these carbons have 4 bonds and 0 lone pairs. So what's their formal charge going to be? 0. Yeah, we don't have to worry about them. Looking at this nitrogen, this is another unique bonding motif. This nitrogen with a group number of 5 has how many bonds attached to it? 2. And how many lone pair electrons? 4. Okay. So a nitrogen with 2 lone pairs will typically have a formal charge of -1. These are anionic nitrogen species. You'll see these a lot in the acid-base chapter. As we've discussed previously from pattern recognition, a nitrogen with 4 bonds has a formal charge of what? +1. Yep. Looking at this carbon with 3 bonds and 1 lone pair, what's the formal charge going to be? -1. Okay, perfect. We're now going to move to some more interesting and unique examples that you'll see later on in this class. Again, we're going to use the same rules and procedures that we've always been. Now, to save us some time, looking at each of these carbons with 4 bonds and 0 lone pairs, do they have a formal charge? No. So we don't have to worry about them. These all have a formal charge of 0. Of course, this is why we don't write formal charges of 0, because it's redundant. We only want to highlight locations with non-zero formal charges. Now, looking at this oxygen atom with 2 bonds and 4 lone pair electrons, what's the formal charge going to be? 0. Yep, just to showcase that, 6 minus 2 minus 4 gives us a formal charge of 0. The only actual charged species in this molecule is this nitrogen here. And would someone like to volunteer the formal charge for that nitrogen? +1, exactly. Okay, perfect. The next species that we're looking at is known as an enolate. There's another way to draw enolates, as we'll see in the resonance chapter. As customary, all of these carbons with 4 bonds and 0 lone pairs have formal charges of 0, except for the carbon with a lone pair. And looking at this bonding arrangement, what is the formal charge of this carbon species? -1. Okay, perfect. Finally, looking at this oxygen with 2 bonds and 4 lone pairs, what's the formal charge? 0. Okay, perfect. Ideally, you want to practice these calculations enough where you can quickly assign formal charges just looking at the molecule. This will save you time and is especially important in thinking about reaction mechanisms. Okay, in this next example, let's highlight how to do this calculation for expanded octets. The formula remains the same. So looking at this sulfur, let's dissect it in detail. What is sulfur's group number? What group is sulfur in the periodic table? 6, yep. How many bonds are attached to sulfur? 5, yep. This is known as an expanded octet structure. Does this sulfur have any lone pairs? No. So then, what is the formal charge on this sulfur? +1. Exact same calculation method. Okay. Now, are there any other atoms in this structure? Let's try to identify and look for atoms with a non-zero formal charge. What atom does not have a non-zero formal charge? What atom has a formal charge? Oxygen. This bottommost oxygen. And what is the formal charge on this bottommost oxygen? -1, exactly. This is an intermediate and is often a common structural motif found in sulfur ylides that you may see in Chem 113. This last structure is an analog and structurally similar to many common Wittig reagents. Again, just like before, let's handle and let's do this calculation for the formal charge on phosphorus. So, what is phosphorus's group number? 5. And how many bonds are attached to phosphorus? 4. Okay. Does phosphorus have any lone pairs in this drawing?
No.
Nope. So it has a formal charge of +1. Now, are there any other atoms in this molecule with a, yep, the lower carbon? And what's the formal charge on this lower carbon? -1. Where did we get that from? Carbon has a group number of 4, has 3 bonds and 2 lone pair electrons for a formal charge of -1. Now, let's try to explain this thesis. Let's try to use our idea of bond electronegativity and try to rationalize why are we putting the negative charge on carbon in this structure? Why is that a reasonable resonance depiction? Why is this a reasonable depiction of this molecule? And I'd like to really highlight, if we look at the carbon-phosphorus bond, carbon is actually slightly more electronegative than phosphorus. So the bond's polarized towards carbon. Always want you, when you look at a structure, to try to think, why is that drawn the way it is? What principles can I use to explain this drawing? Does this make sense? Always try to use the concepts that you've discussed. Any questions on formal charges? I know we're doing a lot of drills on this. The reason being, in the acid-base chapter, we're going to be putting formal charges on our molecules pretty quickly, and I want to make sure everyone's comfortable with it. Yes?
Why do you have the charges? You say something about them being activated or something like that.
So in many reactions, often protonation, adding a hydrogen, bonding a hydrogen to different atoms, or Lewis acids interacting with a lone pair can result in generation of a positive charge on certain atoms, which changes the reactivity and overall susceptibility of the molecule to attacks from nucleophiles, etc. It's mainly a means of making intermediates more reactive, or protonation can overall potentially change molecular shape, and it can definitely change how polarized, like how the electron density is distributed and pulled across bonds in a molecule. Yeah. So formal charge helps represent regions of localized electron density. Okay, let's continue on. So as we looked at in that sulfur example, that was one case of what are known as expanded octets. And the rule for expanded octets is any element with n equals 3 and above have access to L equals 2 orbitals. So as we're thinking about orbitals, the L equals 2 orbitals are known as our quote unquote d orbitals. And because we have access to these d orbitals, we can utilize these d orbitals in hybridization and in bonding. So anytime you're in n equals 3, and farther down on the periodic table, these elements can potentially form more than just 4 bonds. They can form an expanded octet. The primary culprits, as we'll see in a moment, are sulfur, phosphorus, and chlorine, or higher order halogens. So the general rule is to minimize formal charges, double and triple bonds can be formed that would lead to an expanded octet structure. So one of the main goals when we depict and utilize or invoke expanded octets is to draw structures that minimize formal charges. So let's look at sulfuric acid, H2SO4. So hydrogen contributes 1 electron and we have 2 hydrogens. Sulfur contributes 6 electrons and we have 1 sulfur. And oxygen contributes 6 electrons and we have a total of 4 oxygens. Adding up our total, we get a total of 32 electrons to work with. Now, what is our most plausible central atom? What is our least electronegative atom? Sulfur. So we're going to put sulfur in the center, and we're going to surround it with our 4 oxygens. Now, you can really think of hydrogens from the perspective of drawing Lewis structures very similar to a lone pair. They're worth, a bond to hydrogen is worth 2 electrons. So we're going to decide to distribute our hydrogens on our outermost atoms. So where do we want to put our hydrogen? On an oxygen, exactly. So let's do just that. Okay, as per our standard protocol, what's the next step? What's our next step? 1 bond each. Yep. 1, 2, 3, 4, 5, 6. We formed a total of 6 bonds. So we've used up 12 electrons. We now have 20 electrons to work with. Okay, so far so good. Now our next step is to take these 20 electrons and assign lone pairs. So where are we going to place our lone pair electrons first? On the oxygens, okay? And looking at this oxygen down here, it has a total of 2 bonds or 4 electrons to its name. How many additional lone pairs does it need? 2 lone pairs for additional 4 electrons. 1, 2, 3, 4. This top oxygen is exactly the same, needs 4 electrons. Okay, what about the oxygen on the left here? How many lone pairs does it need? Well, 6 electrons, 3 lone pairs. Yep. 2, 4, 6, 2, 4, 6. So in total, we've used up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We've used up all 20 of our electrons. Now, this is the structure that you'd probably have drawn for sulfuric acid in 101 or 102. It fulfills the octet rule for sure, but if we take a look at our formal charges, is there a problem with our formal charges? Let's take a look. What is our theoretical formal charge? What is our theoretical formal charge on this leftmost oxygen? What's our theoretical formal charge? Just utilizing pattern recognition. What was that? -1, exactly right. We have a formal charge of -1 on each of these oxygens. And looking at sulfur, what would the formal charge be on sulfur in this case? Let's calculate it. Sulfur has a group number of 6, and how many bonds are attached to sulfur? 4. So then it has a formal charge of +2. Now, when we discussed our formal charge rules, do we prefer large or small formal charges? Small. So to get rid of this +2 formal charge, how many bonds do we need to make to sulfur? 2, exactly. And do we have some convenient lone pairs that we want to use for bonding? Yes. So what we're going to do, instead of going with this structure, is we're going to kick down these lone pair electrons. And our goal, and the result of this process, is by forming these double bonds, we have eliminated our formal charges. So this final structure, let me draw this in the exact same orientation. So looking at this final structure, we have eliminated our large formal charges by invoking an expanded octet. Now, would we be able to do this if we had oxygen as a central atom? No. And the reason being is only elements in n equals 3 and below have empty d orbitals that they can use for expanded octet bonding. Okay. So, does that make sense to everyone on why we invoke expanded octets? Let's look at another example, and this time I'd like you to give this a shot. We are dealing with periodic acid, which is a relative of perchloric acid. It's an oxidizing acid, and it's quite dangerous to handle with organic compounds. I'd like you to draw a valid Lewis structure, keeping in mind formal charge rules and invoking an expanded octet when appropriate. Any questions so far? Oh, if you're correct in moving try to look at each oxygen individually. And you're correct in moving each of these oxygens that are minus 1 from each other. Iodine is plus 3. And when we have those charges right next to each other, we want to minimize from each other. One way we can do that is by adding bonds. Any questions? Any questions? Everything going okay? In general, we prefer to place hydrogen in oxygen for the more electronegative atoms. Any questions? Okay. Any questions? Yep, that's good. Perfect. So, just to keep things moving, I saw a lot of reasonable responses so far. So let's take a look at this structure. And first and foremost, let's do some electron counting. Hydrogen contributes 1 electron to this process. Iodine contributes a total of 7 electrons. Oxygen contributes 6 electrons. And we have how many oxygens to work with? 4. Okay, perfect. So, adding up our total, we have 32 electrons in our structure to work with. Now, following this, what are we going to place as our central atom? What's the least electronegative atom? Iodine, yep. So we're going to place iodine as our central atom, and we're going to surround it with our oxygen atoms. In general, for most structures, you're going to attempt to bond hydrogen to the most electronegative atom whenever possible. So what are we gonna bond to hydrogen? Iodine or oxygen? Oxygen. Okay, perfect. Our next goal in this process is to form 1 bond each. 1, 2, 3, 4, 5. Okay, so we formed a total of 5 bonds, and we've used up 10 electrons. So from our 22 electrons remaining, let's now try to fulfill the octet of every single atom in this molecule using lone pairs. So let's switch to our lone pair color. And how many lone pairs do each of these oxygens with just 1 bond need? How many lone pairs? 3. Yep, 3. 1, 2, 3, 4, 5, 6. 7, 8, 9 lone pairs for a total of 18 electrons. So we have only 4 electrons remaining. Where do those last 4 electrons go? Is there an atom with an incomplete octet? The oxygen, yep. So it needs 1, 2 lone pairs for a total of 4 electrons. Perfect. So we are out of electrons right now. However, even though we fulfilled the octet of every single atom, do we have a formal charge issue to worry about? Yes. So let's take a look at our formal charges. So first and foremost, each of these oxygen atoms have a formal charge of -1. Let's delve in and let's look at iodine in detail. So let's look at that iodine atom in detail. So what is iodine's group number? 7, okay. And how many bonds are attached to the iodine? 4. Okay. Does it have any lone pairs? Does iodine have any lone pairs? No. So then that gives us a formal charge of +3. That is a large formal charge. So we have a positive formal charge and a negative formal charge adjacent to each other. Can we form bonds to minimize these formal charges? Yes. So we're going to form bonds using each of these negatively charged oxygens lone pairs. So we're going to kick down 3 sets of electrons to form a total of 3 double bonds. And the reason why we're trading in one of our lone pairs for a double bond is that would eliminate this negative formal charge. Does that make sense to everyone? So let's draw our revised structure for periodic acid. Perfect. And in this structure, we have invoked an expanded octet and we've minimized our formal charges. So you primarily see this with halogens such as chlorine, bromine, iodine. Can we see this kind of behavior with fluorine? No. And the reason being, it is in the second group. Yeah, exactly right. Any other questions on expanded octets? Okay, let's keep going just to check time here. We still have a little bit of time to work with. So let's keep going. So let's do a few examples where we cover some expanded octet structures. I'll start us off. This first structure, we have CH2 with a phosphorus containing 3 CH3 groups. So again, let's try to always utilize our condensed formula rules for quickly writing Lewis structures. So what's the first structural motif that I should draw? Yep, a carbon with 2 hydrogens attached. Okay, and what is attached to that carbon? Phosphorus, okay? And following our formula, what is attached? What is attached to our phosphorus? Yep, a carbon with 3 hydrogens. Yep, so we have a CH3 group. Now, looking at this subscript, there's a 3 behind our CH3 group. So how many CH3 groups do we have attached? 3. Yep, exactly right. Perfect. Okay, now we have our skeleton in place. Let's do some quick electron counting math. So from our carbons, from all of our carbons in this structure, we have 4 carbons, each of them contributing 4 electrons for a total of 16. We have a total of 11 hydrogens contributing a total of 11 electrons. Finally, phosphorus contributes how many electrons to our total? 5. Okay, perfect. So adding this together, we have a total of 32 electrons to work with. How many have we used up in drawing our skeleton? How many have we used up in drawing our skeleton? Yep. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. We used up 30 of our electrons. We only have 2 electrons remaining. Is there an atom with an incomplete octet? The first carbon. So are we going to put the lone pair on that carbon? Yes, exactly right. I really like this skeleton followed by electron counting method, as we can quickly generate our scaffold and then fill in our double and triple bonds by carefully counting electrons. Now, this structure is perfectly fine to draw. We've in fact seen this before in an earlier example. However, looking at our formal charges, do we have formal charges in this current depiction? Yes, we have a formal charge of +1 on phosphorus. And what about carbon? -1. Just as a refresher, 4 minus 3 minus 2 gives us our formal charge of -1. So although this structure is pretty good, it's pretty descriptive, if we wanted to minimize formal charges, what will we do between this carbon and this phosphorus? What are we going to? Exactly right. We are going to take this lone pair and we are instead going to form a double bond. Now looking at this structure, have we minimized our formal charges? Yes. And the reason why we can do that is because phosphorus can adopt an expanded octet. Yes.
So is it safe to say that because like 1 and -1, they're not large compared to like
Yes.
the last ones
Yeah.
and the 2? So is it safe to say that if an element is under the N3
Yes.
row, we just always get rid of the formal charges even if it's 1?
Yes. Your goal is to mitigate formal charges. This is one way of drawing this structure to better showcase a Lewis structure without formal charges. In reality, this lone pair and our first depiction with our lone pair on carbon is more useful for thinking about reactivity, but nonetheless, this structure with minimized formal charges really helps us see that this carbon-phosphorus bond has a lot of properties similar to a double bond. It's not a single, it's more similar or more akin to a double bond in terms of length and strength. And that's really the beauty of these structures. If you draw structures that minimize formal charges, invoking the expanded octets, you can better get a sense of how strong a bond is and how long a bond is.
And just
Yes.
for recap,
Mhm.
the double bond is weaker than the single bond, right?
Double bonds are stronger typically.
I thought the triple bond was like the stronger, double bond was just the single bond was stronger.
In general, bond strength increases with bond order. The more electrons you have shared between two atoms, the stronger that interaction. The more electrons you have shared in bonding electrons between atoms, the stronger the bond. Does that make sense? Perfect. So we're unfortunately out of time for today, but we'll continue on with this next class session, and we'll go a little bit faster next session.